Hello everybody. In this video we are going to be looking at refraction. So in our last video we looked at reflection, and if you remember, reflection is when you have a ray of light that is traveling through a transparent medium such as air, and it strikes the boundary between another medium that is not translucent or that it cannot travel through. That ray of light is going to bounce back or reflect back into that first medium. If a ray of light is traveling through a transparent medium, again, let's say air, and it strikes a boundary to another medium that is also translucent or that the light can travel through, then part of that ray of light is still going to be bounced back into the first medium, but another part of that light or that ray of light is going to then cross that boundary between the two mediums and travel through that second medium. A good example of that is if you have light coming through a window. You have light traveling through the air. It reaches the boundary between the air and the window, but because the window is also translucent to light waves, that ray of light is going to then continue to travel through the window. Some of it will bounce back into the air, but a good chunk of it or a majority of it is going to pass through that boundary and then travel through the window. When it crosses that boundary between the air and the glass, the ray of light is going to bend, and that is because the light is going to travel at a different speed through the glass than it does through the air. Light does travel at different speeds through different mediums. So when we reach that boundary, the ray of light is going to change its direction slightly or bend, and that bending of the light is what we call refraction. Let's take a look at a diagram of refraction. If we have an incident ray of light, here's my incident ray coming down in that direction, and it reaches the boundary between, first of all, the incident ray is traveling through air, and it reaches the boundary between air and glass. When this ray of light reaches that boundary, part of the ray of light is going to reflect back into the first medium. So we are going to have some reflection of that ray. However, some of that ray of light is also going to travel down through the glass. And when we cross the boundary between the air and the glass, we can see, and let me remove some of my markings here, we can see that the ray of light bends slightly at the boundary. We can see that the ray of light, if I want to draw this so that it was going straight all the way through, it would look something like that. Hey, that's a pretty good straight line. I might actually have to save this for posterity. But we can see that the ray of light doesn't do that when it crosses the boundary from the air to the glass. It bends. So we have, just as we did before, we have our angle of incidence, and we always measure these angles from the normal. So the angle of incidence is the angle between my incident ray and the normal. Then I have my angle of reflection, which is right here. That is the angle between my reflected ray and the normal. But I also have my angle of refraction, which is right here, and that is the angle between the refracted ray and the normal. And remember, we always draw our normal perpendicular to the plane of the surface that the ray of light is either reflecting or refracting through. So all those measurements are from the normal, but now we do have another angle that we have to take into account, and that is called my angle of refraction. And the angle of refraction, which is going to be different from my angle angle of incidence and my angle of reflection, depends upon what this medium is. And like I said before, light is going to travel at different speeds through different mediums, and how much it refracts depends upon the properties of that particular medium that it is refracting into. Okay, this is just a diagram of an actual ray of light traveling through a lucite block. A lucite block is just something that is transparent to light. So we have our incident ray, which is number one, traveling from some source. When it reaches the boundary between the air and the lucite block, right about here, that's not working very well, is it? Let me just try a different color here. I thought that was yellow. Let's try yellow. All right, right here, that doesn't work either. Well, you guys can see where that is. All right, when the incident ray reaches that boundary between the lucite block, part of that ray, incident ray, is going to be reflected back into the air, which is what the ray that is marked number 2 indicates. The majority of that ray of light, however, is going to pass through the boundary between the air and the lucite block and start to travel through the lucite block. We can see how the ray of light bends as it goes from the air into the block. When it reaches the bottom of the block, because it's sitting on a table or some surface that is going to be opaque and light can't travel through, it is going to reflect back into the lucite block, which is what ray number 4 is. And then when that ray that is reflected off of the bottom of the block reaches the top of the block and the boundary between the air and the block, it is going to refract back out of the block and into the air, which is represented by ray number 5. One thing I do want to note on this drawing is that note that rays 2 and 5, my original reflected ray and my final refracted ray, are parallel to each other. So the geometry kind of works out neatly, and we'll talk a little bit more about that later on. The angle at which light refracts from the normal depends upon a couple of things. The first thing it depends upon is the material that it is traveling through, and it could be a number of different things. There's lots of different materials that are translucent to light. There's glass, there's plastic, there's like the lucite that we had in the previous slide. So it depends upon the material that it is refracting into, and it also depends upon the angle of incidence. So at what angle does the ray of light strike the boundary between the two mediums? And we could represent that mathematically by saying the sine of theta 1, by the way, is my angle of incidence, theta 2 is my angle of refraction. So the sine of my angle of incidence divided by the sine of my angle of refraction is equal to the speed that light is traveling through in my refracted medium divided by the speed that the light is traveling through in my incident medium. And that is always going to be some constant value. And we will talk about what that constant value is coming up in a few slides. But just note that that refraction is reversible. Say you have a window in your house and you look outside your window, as the light travels from outside and it travels from the air outside to the glass, it's going to refract in the glass, and then when it gets to the other side of the glass and it refracts from the glass back into the air, that angle is going to be slightly reversed. And because windows are very, very thin, it only refracts or offsets your image that you're looking at through the mirror by just a very, very small amount, but it does offset that a little bit. A couple of things that we know about refraction. Remember that the speed at which light is traveling is going to be different for the two mediums. So if light is traveling from a medium where it is moving fast into a medium where it is moving slower than the first medium, so my incident medium is, light travels faster in my incident medium than it does in my refracted medium, the ray of light or the refracted ray is going to always bend toward the normal. So my angle of refraction is going to be less than my angle of incidence. So in the case of this diagram, light will travel faster in air and slower in glass. So it's going from fast to slow. And when it does that, it is going to bend toward the normal. When light is traveling from a medium where it's moving slower into a medium where it's going to be moving faster, my refracted ray will always bend away from the normal. So when I go from a slower medium to a faster medium, my refracted ray will always bend away from the normal, and my angle of refraction will be greater than my angle of incidence. So in this case, we have the ray of light starting in glass and then traveling into air. So it travels slower in glass than it does in air. So when it goes into the faster medium, the ray of light is going to refract away from my normal. As I mentioned, light will travel at different speeds in different mediums. We know in a vacuum that light will travel, excuse me, at 3.00 times 10 to the 8th meters per second. That is our universal speed limit according to our friend Mr. Einstein. the ratio between how fast light moves in the medium compared to how fast light is moving in, I'm sorry, let me start that over again. The ratio between how fast light is traveling in a vacuum compared to how fast light is traveling in any particular medium is called our index of refraction, and it is represented by the variable n. So the index of refraction equals the speed of light in a vacuum, which is our value for c, which is 3.00 times 10 to the 8th meters per second, divided by how fast the light is moving in a particular medium, which is just represented by our velocity v. Note that because we are taking a speed and dividing it by a speed, our units are going to cancel out, and our index of refraction will be a dimensionless or unitless factor. So there's no units attached to our index of refraction. So as I mentioned, our index of refraction in a vacuum where there's no air, remember that the speed of light is going to be 3.00 times 10 to the 8th meters per second, because I have c divided by c, which is going to equal 1. For any other media, my index of refraction has to be greater than 1, because I'm going to have c divided by v. I know that v can never be greater than c. Right, my speed of light can never be greater than 3.00 times 10 to the 8th meters per second. That is my universal speed limit according to Albert Einstein. And I ain't arguing with that dude. He was pretty smart. So every other medium other than a vacuum, my index of refraction is going to be greater than 1. And that's a good test. If you ever try to calculate an index of refraction for something and you get a value less than 1, it means that something went wrong somewhere and you need to go back and double check and see where you made your mistake. And as I said before, my index of refraction does not have any units attached to it because we are dividing a speed vector by a speed vector. So my meters per second will always cancel out. So n is a unitless ratio. This table shows us some common indices of refraction for some common materials. This is, by the way, a very, very good slide to keep handy and bookmarked as you guys are doing problems over the next few days. You know how I always say in every PowerPoint, there's one slide that's important that you need to have access to. This is that slide. So just to show you some indices of refraction, remember the greater the index of refraction, the slower the light is going to be traveling. So we have a diamond has an index of refraction of 2.419. We have glass, and there's different types of glass. We usually default to crown glass, which has an index of refraction of 1.52. So if I just say, and I try to be specific in most of the problems that I'm going to be giving you, but if I just say glass, you always default to crown glass of an index of refraction of 1.52. Cubic zirconium or zircon has an index of refraction of 1.923, and notice that the index of refraction of zircon or cubic zirconium is less than the index of refraction of a diamond. So ladies, if you ever get any bling from a guy at some point in your life and you want to know if the ring is real, you just got to test the index of refraction, and that'll let you know if this guy is worth marrying or not. Some other common indices of refraction for air, note that air is slightly greater than 1, but not by a lot. So it's 1.000293. And because we usually round things to 3 significant figures, we're usually going to say that air is going to have an index of refraction of 1, even though it's not a vacuum technically. We have to, in order to get the value of the true index of refraction, we have to take it out to at least 5 significant figures, and we don't usually do that. So for our purposes, we could say that air has an index of refraction of 1. Next, I want to talk about Snell's law of refraction. And let me just tell you guys a quick little story. My first year at Shelton, which was about 6 years ago, I'm going over this PowerPoint with my students, and I start talking about Snell's law of refraction. And I'm like, what the hell kind of name is Snell? Who has a name like Snell? How come these things aren't? How come there aren't any scientists named Bob? What about Bob's law of refraction? And one of the kids kind of raised their hand and said, you know, there are 2 teachers here in this school who are named Snell. And I said, oh, never mind. just disregard everything I just said. So we love Snell's law of refraction. I have no idea if it's connected to our Snell's in any way, but it'd be pretty cool if it were. But let's take a look at what Snell's law tells us. It tells us that the index of refraction for my incident medium times the sine of my angle of incidence equals the index of refraction, my index of refraction for the second medium times the sine of the angle of refraction. So n1 sine theta 1 equals n2 sine theta 2. And all that means is if I take my value for n for my incident, oh, that's an ugly n. Hold on here. If I take my value for n for my incident medium and multiply it by the sine of my incident, my angle of incidence, that has to equal the index of refraction for my refracted medium times the sine of my angle of refraction. Pretty simple formula. Just one quick note, because we are dealing with our trig functions here, always make sure your calculator is in degree mode and not in radians. I'm not going to be there to remind you as you're working through these problems. So just make sure you're in degree mode for these problems. All right, let's talk about how refraction is responsible for the creation of rainbows. Now, I have explained a lot of things to you guys over the course of this past year. I have explained walking and how walking works. I have explained doors, how doors work. I've explained a lot of other things to you guys. I've opened your eyes to a lot of things, and I thought the last thing I would really explain to you are rainbows. What's better than a rainbow? All right, so let's talk about how rainbows are formed. We know that a ray of light will strike a drop of water in the atmosphere, and when it does strike that drop of water, it's going to cross the boundary between the air and the water. And when it does that, it is both going to reflect and refract. So it's going to refract at the front side of the water droplet. So when the light first hits the water droplet, it's going to refract as it travels from the air into the water. Now, different wavelengths of light are going to refract at different angles. So the violet wavelengths are going to refract or have the greatest angle of refraction, and the red wavelengths are going to have the smallest angle of refraction, and all the different colors in between those two will refract at different angles. So here we have a diagram of a water droplet, and we see that we have some rays of sunlight that are intersecting with this water droplet. Now you can see here that my violet rays are going to refract more than my red rays. So the violet rays are going to refract at a different angle or have a greater angle of refraction than the red wavelengths of light. When all those wavelengths of light hit the backside of the raindrop, they are going to reflect back into the raindrop. So they're going to enter on the front side of the raindrop. They're going to refract. Then when they hit the back side of the raindrop, they're going to reflect back into the raindrop. And when they get back to the front side, they are going to refract again. And again, the violet wavelengths are going to refract the most, and the red wavelengths are going to refract the least. After all of that refraction and reflection, the angle between the incoming sunlight and the violet rays that are leaving the raindrop are going to be about 40 degrees. The angle between the incoming ray of sunlight and the refracted red wavelengths is going to be about 42 degrees. So we've separated out the different wavelengths of light. So for the raindrops that are higher up in the sky, you are going to see all of the red wavelengths from that raindrop, from that droplet of water. The violet wavelengths are going to travel over your head. For the water droplets that are lower in the sky, you are going to see the violet wavelengths refracted from those drops, and the red wavelengths from those drops that are lower down in the sky are going to go below your eyes, and you won't see those wavelengths. And then for all of the water droplets that are between the upper and the lower ends are going to refract, or different wavelengths are going to reach your eyeballs. So that's why you see all of those different colors in a rainbow. It's just the light refracting at different angles from all of the different water droplets in the sky, from higher up to lower down. And that's how rainbows are born. You're welcome. One last thing I want to talk about with you guys, and that is a concept known as total internal reflection. If we have a ray of light that is going from a medium with a higher index of refraction into a medium with a lower index of refraction, in other words, if light is traveling from a medium where it is moving slower into a medium where it is going to move faster, remember that as we increase my angle of incidence, my angle of refraction is going to increase as well. My angle of refraction is always going to be greater than my angle of incidence, because when we go from a slower medium to a faster medium, the light is going to bend away from the normal. At some point, we are going to get at an angle of incidence where all of my light is now, because the Snell has to bend away from the normal, all of my refracted light, or all the light, is going to be refracted at an angle greater than 90 degrees. And when that happens, all of the light is going to reflect back into the first medium, and none of the light will cross the boundary into the second medium. And we call that total internal reflection, because again, all the light is reflecting back into the medium. And that's simply because once my angle of incidence gets great enough, my angle of refraction is going to be greater than 90 degrees, because when we go from a slow medium to a faster medium, my refracted ray is always going to bend away from the normal. Now, when we're going from a medium where the light is traveling slower into a medium where the light is traveling faster, we're going to get at a certain angle of incidence that will give me an angle of refraction of 90 degrees. In other words, all of the light is going to just stay at that boundary between the two mediums. We call this the critical angle. Any angle of incidence that is less than the critical angle, I will have some light travel into the second medium. Any angle of incidence greater than the critical angle means that all of the light is going to reflect back into that first medium. And to find out what the critical angle is, I'm trying here, people. I'm so close to the end. I'm going to try that again. To find the critical angle, I know that the sine of my critical angle is equal to the index of refraction of the second medium divided by the index of refraction of the first medium. And the second medium is going to be my my refracted medium, where the index of refraction is going to be less than my initial or incident medium, where I'm going to have a greater angle of, or index of refraction. So to find the critical angle, it's simply the sine of the critical angle is going to equal the index of refraction for my refracted medium divided by the index of refraction for my incident medium. And my index of refraction for my incident medium always has to be greater than my index of refraction for my refracted medium. Otherwise, there will be no critical angle, because then my refracted ray won't be bending away from the normal. Just to summarize, whenever I have angles of incidence that are greater than my critical angle, all of light is going to reflect back into my incident medium. It's going to reflect back into my first medium, and none of it's going to cross the boundary between the two mediums. And that's simply just obeying the law of reflection. So we're still working with our law of reflection. And I can only have total internal reflection when I'm going from a medium that has a higher index of refraction to a medium that has a lower index of refraction. If I'm going from a medium where light is moving slower into a medium where light is going to travel faster, because that way my my angle of refraction, or my refracted ray, is always going to want to bend away from the normal. So we have to meet those two conditions in order to get total internal reflection. One very useful application of total internal reflection are fiber optics. Fiber optic cables are used in communications, and whenever you send, make a phone call or send a text or use your phone to try to communicate with anybody, at some point that signal is probably traveling through fiber optic cables somewhere. So there's a lot of great applications to fiber optics. I have a lot of great demonstrations that I usually do if we were doing this in class, and I'm bummed that I can't show you guys that. But that is just one way in which we can take a ray of light and have it travel along like a thin glass or plastic tube, and it's going to stay within that because the light is always going to be hitting the boundary between the fiber optic cable and the air surrounding it at an angle greater than the critical angle, so it is always going to reflect internally and never pass out of the fiber optic cable. And we can send light signals of very, very long distances through that. We can have it bend around corners and go around curves and do all sorts of very, very cool things. So that is just one application of total internal reflection. Hey guys, that's it. We're done. I have nothing else to teach you. I have reached the end of physics. You made it. Congratulations. This is the end. No more new stuff after this. We're done.